All right, our lab is that of Newton's laws. Our investigation question is, what will happen to the acceleration of the system when the mass of the system is constant and the force applied to the system changes? What do we already know about this test subject? We already know that the acceleration of the system is the ratio of the total force over the mass of the system, according to Newton's second law of motion. We already know the friction on the cart is minimal, but there is some friction in the pulley, so it is not a completely frictionless system. We hope that this experiment will tell us the effect of changing force and constant mass on acceleration, and show us the effect of a pulley with friction on how it impedes our theoretical value of the acceleration of the system. Our claim is that the acceleration will have a directly proportional relationship to force, so as force increases, acceleration increases, and as force decreases, acceleration decreases. However, this will not be a perfectly proportional relationship because of the friction in the pulley.
The materials we used for this lab were a Chromebook with SparkView, a Pascal motion detector, a lab notebook, flat motion track, assorted masses, a low-friction pulley, and a string. The independent variable for this lab is the net force exerted on the cart, and the dependent variable is acceleration of the cart. We measured the dependent variable using a motion sensor and SparkView. Our procedure was 1. Set up SparkView. 2. Place a track on a flat table with the pulley extending past the table. 3. Place a sensor on the track across from the pulley. 4. Place a cart on the track with the string hanging over the pulley. 5. Choose a system mass as a control to distribute between hanging on the string and in the cart. 6. Hold the cart to make sure it doesn't move before it is released. 7. Release the cart. 8. Use the graphs from SparkView to determine the acceleration. 9. Repeat steps 4 through 8 3 times and determine the average acceleration. 10. Remove 50 grams out of the cart and place the removed mass on the string, ensuring the mass of the system stays the same. 11. Repeat steps 4 through 9 as many times as you like. 12. Use a scatter plot to determine how changing the net force of the system affects the acceleration of the cart.
As you can see from the graph, clearly this data supports our claim, because as the force increases, the acceleration increases, and as the force decreases, the acceleration decreases. This proves that the acceleration of a cart, when the mass of a system remains constant but force is varied, is directly proportional to the force. This is shown in both the theoretical data and the experimental data. Some of the problems that may have occurred with this procedure is systematic error. First off, the pulley cart system may not have been functioning properly, and the string may have been cut or not the same length after each trial. Furthermore, another problem that may have occurred with this procedure would be random error. The timing of the release of the car may not have been identical to the start of the Pascal motion detector. Also, the car may not have been launched from the exact same point each time. To resolve the first problem of the string being the same length, we made sure that the string was as straight as possible each time. Also, we would level the cart as best as we could to make the cart go straight. Finally, to fix the problem of not being launched from the exact same point, we marked a point on the track where we released it every time. Furthermore, we would start the program on the computer, the SparkView program, earlier than the release of the cart. This would allow the detector to find the cart and also limit the amount of random error occurring with the motion detector. For future investigations involving this study subject, some ideas we have are to use a track that is actually frictionless. Although the metal track has minimal friction towards the cart, this minimal friction could make a large difference. Also, we could perform this experiment in a confined area with no air resistance, so the cart would have no external forces acting upon it. Furthermore, this confined area would minimize the amount of error of the Pascal motion detector because of the many people and actions occurring around it during this experiment.